Once again, we have here Dr. Alexandre Emerick, who entertained us about ensemble-based data simulation in large-scale petroleum reservoir models. Okay, the floor is yours. We're gonna have 45 minutes plus a Q&A section. Thanks.
Okay. Thank you very much, Professor Alvaro, for the invitation. Thank you for the very nice introduction. I'm going to spend the next, I don't know, maybe 30 or 40 minutes talking about a topic that has been part of my professional life for the last, since 2008, so maybe 19 years. Yeah, 18 years. Which is ensemble-based data simulation, and I work for petroleum industry, so the kind of application I'm going to show is in petroleum reservoirs, but this is a sort of problem that happens in many geoscience applications. Before I start talking about data simulation, I should say a few things about reservoir simulation, which is of course a numerical model of reservoirs. Is typically based on volume difference or finite volume or finite difference. And reservoir simulation, I would say, is the main tool of reservoir engineers, which they use for making comparisons between production strategies, to making production forecasts in fields. For example, we usually try to optimize the positions for drilling wells. So we do reservoir simulations for comparing different scenarios. We try to do, what else? We should decide whether we want to inject water or gas, where I'm going to inject water or gas. We compare different enhanced oil recovery strategies. So reservoir simulation is something really important for reservoir engineers, for petroleum reservoir engineers. However, building reservoir models is a complicated task. It's a task that involves different disciplines and involves different types of data. The typical workflow, I'm trying to illustrate a typical workflow for building a model, but it of course varies case to case. I'm just going to emphasize a few elements that they're sort of always present when you're trying to build a model. Very often we start from seismic. We do seismic interpretation, so we can build like a structural model of the reservoir. So this is like a geometry of the reservoir, position of faults, like in this picture. Then at some point, people are going to start analyzing data from wells, so drill wells in our fields. So we get data from logs and also core samples, so get rock samples, and then we try to characterize the rock types you see in this reservoir. You also try to come up with correlation between rock properties. For example, like in this picture, defining correlations between porosity and permeability of the rock for different rock types. And at some point, a geologist will start building what we call a three-dimensional geological model. This three-dimensional geological model has lots of things it has to do, but one of the most important is the distribution of facies. And by facies, I mean rock types. So we, based on previous analysis, we decided there is 3 or 4 different types of rock, depends on the environment as well. And then we define this facies modeling. And then for each facies type, we has to come up with distribution of rock properties. For example, distribution of porosity, permeability, what else? Initial water saturation, and yeah, so on. Then we got what we call reservoir model, at least a geological reservoir model. However, this model is usually too big for practical use in terms of reservoir simulation. So what we do, we build a coarse version of this model. This is what we call upscaling. So then we get a slightly coarse version that runs a little faster because we're going to have to do so many reservoir simulations. There is a few more data we need to input, things like relative permeability curves, fluid properties, what else? Data from wells, position of the wells, completions, the schedule of opening wells, the control of the wells, like the boundary conditions of the problem. And finally, I got a reservoir model, so I can run a simulation and make prediction of the amount of oil I'm going to produce in my reservoir, for example. The problem is that, there are just not enough information for a complete characterization of all rock properties, such that the same people that built this model, he can generate different versions of the same model, each one with a different prediction of oil production in this field. So we can generate actually a set or an ensemble of realizations of this model. At some point, I'm going to get data from wells. I'm going to start producing this field, and then I have measurements of oil rates, water, gas. Eventually, I have pressure sensors. So I get all kinds of what we call dynamic data, data that evolves with time. And what we realize that our predictions are not in a good agreement with my observations, and then starts what we call data assimilation or history matching. In petroleum engineering, we typically use the name history matching, but we mean the same thing. It's data assimilation. All right. So data assimilation is sort of a iterative process in which I'm going to try to modify properties of my reservoir models. For example, try to modify the distribution of porosity in this model such that my predictions are in agreement with my observations. This is a process that requires lots of simulations, especially because I'm dealing with an ensemble of models. So this is something you want to do in a cluster of computers. Otherwise, it's not going to be practical. And at the end of the day, if you get a good data simulation process, you're going to come up with realizations of my model, which are consistent with my observations, but because they are different, they're going to make different predictions. That's actually because there is still uncertainty. I mean, this is a process built in an uncertain environment. There is lack of information, so I'm always having uncertainty. Even after 20 years of production, I still have a large uncertainty in my model, so I still need to do computations in a, I'm going to call it in a probabilistic way, all right? If I get to this point, then I can make predictions and answer questions that are going to aid the decision makers. For example, I can answer a question like, what's the expected value of cumulative oil production after 20 years of production? Or what's the uncertain range in this production, all right? So this is the kind of questions that reservoir engineers try to answer all the time. All right, I have listed a few, I want to call facts about history matching. The first one is that this is an inverse problem. It's clear from this scenario. It's a problem where I'm trying to estimate the system based on observations, based on data. Actually, reservoir simulation would be my forward problem and history match my inverse problem. And this is a large scale inverse problem because the number of uncertain parameters can be really large. For example, the value of the rock property for each grid cell in my numerical model, it's uncertain parameter. So I may have millions, a few millions of unknown parameters. So it's a large scale problem. Function evaluation, which I mean reservoir simulation, it might be expensive. We have models that run really fast for like proxies of the actual field, but operational models, they run in few hours or eventually a few days. So we're going to be looking for data simulation strategies that can handle, I mean, they do not do too many reservoir simulations, otherwise they're not going to be practical. What else? Relationship between model parameters and data is non-linear. That's obvious. However, it's important to make this distinction because I'm going to introduce methods assuming linearity, and then I'm going to do iterations to solve the non-linearity. There is prior information from geoscientists, which essentially means that my process is not only a process of matching observations. I have constraints in terms of the distribution of rock properties. I should generate models which are consistent with my observation, but still preserve what I can call geological plausibility or geological realism. I mean, I should look at those realizations. They should look like samples of the same distribution of those ones. By the way, the construction of those realizations is typically a statistical process. Is what people call geostatistics. It's based on geostatistics, so it generates. We treat this problem as a probabilistic property from the beginning. All right, and finally, matching the history is not the goal. Of course, the goal is to get better models, so I can make better forecasts. Then I can aid my boss to make decisions. And that's why we always have to quantify uncertainty in our predictions, because he wants to manage risk when we make decisions. If we're going to decide to drill well in a certain position, I should look at not only what the expected value of production, but on the uncertain range, so we can manage risk. All right. Excuse me. Well, that was my introduction. Now I'm going to move towards a few equations, and the goal here is not just to show lots of equations, is to try to how can I say it? Try to emphasize what's going on behind the scenes. Try to show you the kind of assumptions we make to get to the points where we have an operational data assimilation method. All right. So beginning, I'm going to start introducing my notation. It's a very simple notation where I have M, which is a vector containing everything I don't know in my reservoir model. So it's a vector of model parameters. Then I have, excuse me, G of M. G of M is a nonlinear model. It's a nonlinear, oh, excuse me. G of M is my vector of predicted data. Okay, it's the result of running a reservoir simulation. And DOBS is my vector of observation, has the same dimension of my predictions. I'm going to compare predictions with data. And the first assumption I'm going to make is that DOBS, which are my observations, I can divide in two parts. The first part would be the actual information, the true data, which I don't know, of course, but it's the data, it's the information that's inside the OBS, and the noise. Right? So it's like an additive assumption of noise. And I'm going to treat E, my noise vector, as a random variable. Right? Also, I'm going to assume that I have, of course, I have model errors. I have imperfections in my model. For example, I have numerical discretization errors. I have, what else? I have simplifications of the physics. I mean, reservoir simulation is not perfect. And what I mean by not perfect in this sense, in this scenario, would be if I knew the actual value of my model parameters, which by the way, is an abstraction of reality because there is no actual true model. The true reservoir is beneath the earth, but there is a model. And if there was this vector of true values for model parameters, and I run a reservoir simulation with this true value of model parameters, I would get another result that would not be exactly the same as the true noiseless data. It would be the true data plus another noise component that I'm going to call model error. All right. So again, I'm making this assumption of additive sort of model error, which is a strong assumption. It's not really true in reality, but that's what I'm going to use. Then now I saw just algebra. I take DOBS D true plus measurement error. Replace the true from here, and then I get DOBS is G of M true minus model error plus measurement error. And now I make the strongest assumption, which is the expectation of both error terms are 0. In other words, that means my data is unbiased and my model is unbiased. That's the strongest assumption I'm going to make at this point. I could relax this assumption and add a bias term and try to develop expressions of bias term. People did that, but I'm going to tell you in operational settings we basically neglect this bias and try to survive with it. We just do this kind of assumption. All right. What else? I can compute the covariance of my observation vector, and this is just the expression for covariance. But the important part is I can tell you that based on those assumptions, the covariance of observation will be the sum of the covariance of the model error and the covariance of the data error, the measurement error. And I'm going to lump everything to a single matrix called C sub E. So C sub E is a matrix that tells me how much I trust my data. My data in my model, every kind of, how can I say, imperfections in the model or imperfections in my measurements is sort of modeled by this matrix C sub E. And I'm going to say, well, now I'm going to assume that my observations, which is now a random vector because there is a random component associated to it, is a sample from a Gaussian distribution for me given by G of M true and covariance C sub E. If this is true, now that's not true, but that's my assumption. I got this expression for a Gaussian. So it's a constant times exponential of this kind of expression. And you kind of can see in this expression, it's a PDF, it's a probability density function. The random variable is the observation. M true, I don't know M true, but this is the actual reservoir, so it's something, it's a constant over here. Okay, it's given. It's, you know, I don't know. So I'm going to do now, I'm going to look at the same expression from a different perspective. What if instead of assuming that DOBS is the observation, I actually measure those observations? So this now it's given. Then I can speculate over M, about M. and that's what people call likelihoods. So it's the same expression, but now instead of M2, I just get M. Here, my random variable is the model, and the observation, the fixed, the observation is a collection I got from fields. You see, that's the kind of trick we do for building our likelihood function. Then I can look at the Bayes rule, of course. Everything is based on Bayes rule. Bayes rule tells me that the posterior probability density function, which, by the way, is everything that I would like to know, is the posterior, because the posterior tells me the uncertainty in my model after the assimilation of my observations. It's the distribution of model parameters given observations, which from Bayes is P of M times P of the obs given M, P of the obs. This guy, I just told you I'm going to model as a likelihood function. This term, I don't care very much about it, because I can just make it like a normalizing constant, because this is a PDF. Integral of a PDF must be equals to 1, so I can replace this guy by the integral of these parts, such that the integral is 1, because this is the integral over the random variable, the only one random variable. This is a number, so it's a constant. And why I don't care? I don't care because I'm not going to really write the PDF, because it's really high dimensional. The dimension of M might be something like a million parameters, so it's really high dimension. What I'm going to do is going to sample this distribution. For sampling, I don't need the constant. But the important part is the posterior is proportional to the prior, which tells me everything I know about my model before assimilation, times a likelihood, which tells me the innovation or the novelty brought by the data. All right, so this is the interpretation we do. I got an expression for the likelihood, so now I need an expression for P of M, for the prior. And I'm going to make another very strong assumption that what if I assume that my prior is Gaussian? Assuming that the prior is Gaussian means it's a distribution of mean, I'm going to call it M prior, and covariance C of M. And you can ask the question, well, are parameters from reservoir models Gaussian? And the answer, of course, is not. However, what we can do is to do some sort of reparameterization if they are too far from Gaussian. Very often, I just don't care. I just do as they are. Sample from their distribution and still keep with this assumption. But sometimes they are so far from Gaussian, we have to do some sort of reparameterization. I'm going to discuss this part in the end of this talk. So P of M as a Gaussian, that's the expression for Gaussian. M prior essentially means my best guess about the value of the parameters before assimilation. And C of M tells me about my uncertainty in the values of those parameters. Also tell me how much parameters are correlated with each other. For example, it tells me how much porosity at a particular grid block is correlated over, spatially correlated over the reservoir. Geologists, they model these kind of things when they try to build these models. Okay, that's geostatistics, all right? So I come back to Bayes rule and just replace the expressions. So it's a constant of exponential of this term times the exponential of this term. Because exponential, a product of the same basis, I can just exponential of the sum of the arguments. And then I'm going to call the arguments objective function, O of M. It's a function of M. Okay, M prior is given, everything is given, only M is a random variable. Why I'm doing this? Because look, if I minimize this term, it's inside of an exponential with minus inside. So it means if I minimize O of M, I maximize P of M given the obs. And this is what people call a maximum posteriori. This is well known in the literature. I'm just making like a revision and try to get to ensemble smoother, which is the method I'm going to use. So the maximum posteriori is like it's like a mode of the distribution. It's a peak of the distribution of maximum value of the PDF. I can compute the maximum posteriori by minimizing this expression, and I'm going to tell you right in front that I never use the maximum posteriori. We never use it. First, because we don't really care about a single model anymore. We have to do we have to have lots of models because we have to quantify uncertainties. So the map is just one. There's also other questions like other reasons, because the map tends to be very smooth. But there is one important thing about the map that I want to emphasize, which is the shape of the object, the form, the structure of the object function. If you look at it, it has two parts, of course, one that came from the likelihood, another one from the prior. I'm going to try to make my predicted data close to my observations because I want to minimize it. So I change M such that this is close to this, then I minimize this term. However, every time I change M, I make M far from M prior, so this term increases. In other words, there is a competition between data and prior model. And the interpretation I like to give to this problem is that I would like to get the smallest possible changes in M such that I match data. Why? Because I believe in my geologists, I believe in the geologists and the people can be for me building those models. I want to preserve as much as I can the model. So if I can match data making the smallest change, I have sort of an assurance that I'm not going to, how can I say it, destroy the realism of the geological model. There's another nice reason, which is, you know what, in general, people do data simulation by just minimizing the likelihood, but then here we get like a term. If you look at these problems from the perspective of optimization, which is the kind of things I'm going to do in the following of this presentation, this is a regularization term. This looks like a Tikhonov kind of regularization, and yeah, it helps improves the optimization process. But again, I don't want to do the map. I want to do sampling. And how can I sample a posterior distribution? There are several ways. One way would be Markov chain Monte Carlo or importance sampling, which are rigorous methods in a way that they converge to the actual distribution, so they're really nice. But they suffer from the curse of dimensionality, which means that if I have a high dimensional problem, like reservoir modeling, or a high number of data points, they're going to require too many evaluations of the object of the forward model to get a reasonable sampling. And when I say too many, really too many, I mean millions of simulations, which is not possible unless you replace your simulator by a proxy, by a surrogate model that runs really fast. Then you can do Markov chain Monte Carlo, but of course now you got another approximation, which is replacing the model, the full physics model by a proxy. And of course, building a proxy for a high dimensional model is also something difficult to do. So I'm going to do something different, which is instead of using a rigorous sampling method, I'm going to look for approximate sampling methods. All right. And the sampling method I'm going to use is called randomized maximum likelihood. Randomized maximum likelihood, or RML, it's very simple to understand. It's just I take the same object function from the prior and make only two changes. The first change is I replace my best guess, my M prior, by a sample from the prior. So this is like a model, a realization generated by geologists, a sample. And then I change also my observations by a sample of a distribution with mean the actual observations and covariance C sub E. So it's like a perturbation added to the observations. I got this object function, then I minimize it. If I minimize it, I got one sample of the posterior. If I minimize 100 times, I get 100 samples of the posterior. Of course, if the minimization process, they converge. Sometimes they don't converge, then you have to do again. And you kind of can see the points. Does it sample right? Nope. It does sample correctly if and only if G of M is linear. If G of M is like a constant G times M, which is not the case, but you kind of can see the approximation going on over here. Also, even though it doesn't sample right for non-linear problems, we've been trying to compare RML. People try to compare RML with MCMC, and they notice that it does a reasonable sampling. It tends to get the regions of high probabilities correctly. Sometimes it misses the regions of low probability, but also plausible, but low probability. It misses regions with low probability, but it samples the most important regions of the distribution correct. I will not say correctly, but reasonably, and it's a decent sampling strategy. But the problem is that I have to solve 100 different optimization problems, which is kind of expensive. But if you want to try to do, one idea would be using Gauss-Newton. So Gauss-Newton for minimization, so I have the object function for the maximum posteriori. Gauss-Newton for minimization is just defining a line search. Each iteration we define a line search. In this line search, I have a direction given by what we call Gauss-Newton direction, and there is a step size in that direction. L is like my iteration index. And the Gauss-Newton direction, I'm not going to show the direction, but that's important to me because I'm going to make a few simplifications based on this direction. If you want to derive this expression, it's kind of easy. You just start from Newton's method, in which you assume that this has a quadratic form. And if you look at this, it is really close to a quadratic form. It's not purely quadratic because this is non-linear. If this is linear, this is an actual quadratic form, and this is why Newton's method would converge in one iteration. But you do like assume a quadratic, then you get gradients, you get Hessian matrix, and then you just ignore a few terms which involves double derivatives. Then you get this kind of expression for the Gauss-Newton direction. That's Gauss-Newton. It's everywhere. If you look at optimization, you're going to find this everywhere. And what I'm going to try to call your attention is for this matrix, G. G is what we call sensitivity matrix, or sometimes we call Jacobian matrix. It's a matrix with partial derivatives of my predicted data with respect to my model parameters. And computing G is really painful because you need lots of derivatives. Look, M is high dimensional. G might be high dimensional as well because I may have lots of data points. So compute G is really painful. We can try to do, if you want to do, the best way would be having a joint implementation in your simulator. However, operationally you use commercial reservoir simulator, so you don't really have access to the codes of the simulator. So we actually would like to deal with this process without having to compute derivatives. It's a little bit painful. Even if you have the codes of a simulator and try to implement a joint, it's really messy. It's really complicated to keep a large scale codes, a large scale, a complex codes with adjoint implementations. But yeah, that would be the best way of computing G is without joints. I'm going to do something else. And something else is what we call, finally, and that's what we use, ensemble smoother. And for introducing ensemble smoother, what I'm going to do, I'm just look at Gauss-Newton again and do just one iteration, the very first iteration. In the very first iteration, M0 is equal to my first guess, so this term vanishes. This vanishes, and there is the rest. I'm going to put this inside here and write what is left. And in what is left, I made another approximation, which is I'm going to call the product C of M G transpose by CMD and GCM G transpose by CDD. Those are two cross covariance matrix. This is a covariance matrix between model and data. Tells me how is data and noise model parameters and data correlated, and this is like a autocorrelation. It's a covariance matrix of data, predicted data. So that's the expression, and this is what people call ensemble smoother, which can be derived from very different ways. Actually, this was introduced originally starting from Kalman filters, and from Kalman filters you define what we call Kalman gain matrix, and you find the optimal Kalman gain matrix, and Kalman gain matrix would be something like this term. This part here. This is Kalman gain matrix, but I'm doing a different way. Why? Because I'm gonna use this analogy between Gauss-Newton and ensemble smoother for the next slides, which is for doing iterative process. Ensemble smoother is not iterative; it's just a single application of this equation. I need to explain how you get this matrix. Yeah. Now I need to introduce the ensemble part of the smoother, which is I'm going to estimate this product. Instead of computing actual derivatives, I'm going to estimate the product, direct the product based on samples. Okay, I'm going to generate a set of samples. We call it ensemble of dimension NE. Typical numbers: 100, 200 realizations. More the merrier. But let's say 200 realizations, and then I can compute this matrix with a standard approximation of covariance matrices. You see, it's just have 100 samples of M. So I compute reservoir simulation for each M, for each model, and then they compute these cross correlations here with this kind of approximation. If I want to do CDD, it's the same thing, but instead of M, I got G of M again. All right. Well, that's ensemble smoother. How it works, the geologist gives me 100 samples, 100 models. I run simulation for 100 models, compute these two covariances. This I have to come up with an approximation for this. This is another problem. I'm not going to go into details, but I have to tell you how much I trust in data before I start. And then I apply this equation, update each of those 100 models. So I get 100 samples of the posterior, which is really cool because it's really efficient. That's nice. However, there is one big problem. It does a really bad job in terms of sampling the distribution. And why it does a bad job of sampling? Because G of M is nonlinear, and you kind of can see that from Gauss-Newton, it's just a single iteration for Gauss-Newton with full stop. So I'm trying to solve 100 minimization problems at the same time with a single iteration. That's what I'm trying to do. So it's not going to work if G is too nonlinear. But if G is linear and the number of models is large, it converges to the actual distribution. It samples correctly if G is linear, if the model is linear. But it doesn't do very well for nonlinear problems. So what we're going to do? I'm going to do iterations. And lots of people did what we're going to call iterative forms of ensemble-smoother. Based on this analogy between Gauss-Newton and ensemble-smoother, you can come up with several ways of deriving iterative forms of ensemble-smoother. Okay, I'm using one in particular called ESMDA, Ensemble-smoother for multiple data assimilation, which is, I'm going to call it iterative because it's not really an iterative form in the sense that we have to tell you, we have to specify the number of iterations in advance. You have to say, well, I'm going to do 10 iterations and then do 10 iterations. If after 10 iterations you're not happy with the results, we're going to do, you cannot do the next one. You have to start again with more iterations. And this has to do with the way we derive the method. But there is one nice thing about ensemble-smoother ESMDA. The expression is really simple. It's essentially the same ensemble-smoother expression. You see? The only difference is this constant. It's a number multiplying this matrix. And the reason for multiplying this matrix, this is larger than 1. It's like I'm inflating my covariance matrix of my data, which means I'm trusting less in my data every iteration. And the goal is to make sure that after I do several repetitions of this equation, I don't give too much weight to the data. You remember from this figure, I don't want to unbalance this competition. Okay, I should not give too much weight for data, otherwise I'm going to sample. My sampling won't be very good. I may get a good data match, but the sampling won't be good. And I want to, of course, sample, have a decent sample because I need to quantify uncertainty. Now I have to select alpha, and the way of selecting alpha, I can select any way I want. I have to actually say how many iterations I'm going to do, like this is what I call NE, and say 10 iterations. Typical numbers, actually, 4 to 8 iterations. I'm going to show you some examples. All examples, they run with 4 or 8 iterations. All right, and there is this constraint. The sum of the inverse of alpha must be equal to 1. If you keep this, you kind of not messing with ensemble-smoother. This is why I cannot do the next iteration. If I do 10 iterations, I cannot do the next one because I would violate this condition. And where this condition came from, you can derive it from different ways. We actually derive it using linear algebra, but actually there is a very simple way, which is just looking at the Bayes rule. Bayes rule is a constant times prior times likelihood. Now I'm going to replace the likelihood by a product of likelihood terms to the power of 1 over alpha 1, 1 over alpha 2, and 1 over alpha NE, and NE is the number of iterations. So it's like a factorization of the likelihoods. Because this is larger than 1, this is smaller than 1, so this is like a smaller version of the likelihood. It's people some call it, it's an annealed version of the likelihood. It has similarities with simulated annealing as an optimization method. So this is a product of something which has the same basis. So it's a product that is like the basis times the sum of the exponents. The sum of exponents is over here. If this is equal to 1, I got the same thing I started with, which means I'm not messing with Bayes rule. So that's why we have to keep this one, because I don't want to mess with Bayes rule. All right. Well, that's what we use operationally. It's called ensemble-smoother with multiple data assimilation. And now I'm going to show you a few examples before I move to the end of my talk. I have to apologize because I'm not going to give you too much information about those examples because they are our actual field reservoirs in Petrobras, so I cannot tell you too much about I mean, the values of properties, so that's why I don't have scales, but I think it's enough to show the kind of result of kind of application we do and kind of result we can expect. So this is one field, and what I'm showing here is one realization of the distribution of permeabilities. So hot colors essentially are high permeability regions. So if I inject water, these blues, this small things are like wells. So this is an injector well. So water injecting this well, it goes from this direction, to producer wells. And of course, cold colors mean small values of permeability. So it's like there is less chancing of having fluid transports in these regions of the reservoir. So this is one realization generated by a geologist. So this is prior, and this is the same after data assimilation, posterior. And this is the realization number 200 of the same ensemble, prior and posterior. I want to emphasize two things. First, if you look at all four, they are different from each other, but they all look more or less the same. As you see, you kind of have continuity in the properties. I mean, you don't have like a really noisy distribution of porosity or of permeability. They all have to, they can kind of keep the prior, the spatial correlation between properties, which is nice. Another thing is, if you compare two priors or two posteriors, you see they are very different from each other. There are some similarities, but they are different from each other, which is cool because I want to have different models so I can quantify uncertainty. They are different, but they are all consistent with the observations. So every time I show a picture like this, red dots mean observations, gray curves mean predictions from prior realizations, and blue ones mean predictions from posterior realization. So in this one, you see very, very nice data matches. I mean, I have 200 different models, all consistent with my observations. That's what I'm trying to, that's the goal, all right? After history match, now I can start doing forecasts. Another case, I'm just taking a small piece of the model because I can show you much, but the only thing I want to emphasize is that if you look at the prior and the posterior, again, I have 200 of those. They still preserve most of the features. I mean, you see, lots of things are the same. Some things change, others are the same. And that's important. Why? Because remember that competition, I would like to get a method that make the smallest change in my model such that my model is consistent with my observations. And what I'm showing here is, you see, after data matching, also there is a forecast period. So there is a forecast in this example. So this is my uncertainty in that particular property, which is probably water production. You see, water was not arriving at the wells, then they just arrived, then we start producing lots of water. Right? A third example, this is a little bit different because now I got a property which is really not Gaussian. Look, it's facies. That's what I call in the beginning rock types. So in this model, the geologist tells me that there is 3 types of rock. One which is, I don't know, best reservoir, a yellow one which is intermediate, and a green one which is really bad. Doesn't flow very much for them. It's like a different kind of rock. And kind of can see it's a discrete property. It's more than discrete, actually. It's a categorical property. It's like sand, interlaminate, and shale, different rocks. And I derived expressions based on Gaussianity, based on linearity, and see how we're going to work in this kind of problem. The trick is to do some reparameterization. And there is one very powerful called truncated plurigaussian simulation. Truncated plurigaussian is something that's been in the literature for at least 20 years. It's a geostatistical method in which I'm going to just transform those realizations into Gaussians and then apply Siemens model to update the Gaussians. And every time I run reservoir simulation, I do the truncation. There is a truncation rule that generates the discrete properties. Okay, so that's what I'm showing here. So, and I can update simultaneously phases and, for example, permeabilities. So this is a prior and posterior, and kind of can see that in this case we got strong changes in permeabilities, but again, really nice data match. Sometimes you see you miss a little bit. This is like if you are from petroleum, you kind of can tell what is this. This is gas production. When you start producing a well, sometimes there is a small cap of gas, and you produce this cap of gas, and then we start producing in a plateau of gas. This is what we call gas oil ratio, which essentially means I'm not producing free gas from my reservoir anymore. It's really hard to get this with numerical models because you have to look, to be very discretized around the well to get this kind of behavior. All right, that's the last part of my talk now. I'm going to spend a little bit talking about what's going on right now, what kind of investigation we've been doing. And I select two examples based on deep learning because everybody's talking about deep learning. Deep learning is so cool. Very nice formulations and really impressive results in all kind of areas. So why not try deep learning? And I'm going to choose two examples. One is using deep learning for model reparameterization. So it's just transform model to Gaussian. And the other one is for data parameterization, transforming, modifying the data to something more Gaussian. And why I care about that? It's because sometimes we want to do assimilation of what we call seismic data. Seismic data is a spatial information. It's more complicated than just production data. All right. Deep learning for phases, so it's for model parameterization. By the way, this is a work in collaboration with PUC. If you try to do ensemble smoothing for a model like this one, you see two phases, but look at the distribution of phases. Very complex channels. You are going to be very unlucky because it's really far from Gaussian. Even truncated Gaussian doesn't work very well for this problem because it's really far from Gaussian assumptions. And what we can try to do, we try to apply deep learning to reparameterize this kind of model, right? There are several ways of doing that. We've been trying lots of things. Generative adversarial neural networks and all the kind of variations that there are from GANs. But I'm going to just show very quickly a variational autoencoder, which is my favorite. All right. In a variational autoencoder, we build a neural network that learns how to get a facies model. I got a sample of facies models generated by geologists and learns how to represent in a compact form. People call sometimes latent representation. Okay, and learns how to transform back to facies, of course. And the nice thing about variational autoencoders is that during the process of training this network, we impose a distribution for the latent space, and this distribution is Gaussian, and ensemble smoothers, they work well for Gaussian. That's why I like so much of variational autoencoders. Another reason why I like variational autoencoders is because I understand what they're doing. When I look at the rest of the things, I just don't understand what they're doing. Variational autoencoders are easier to make analysis. And yeah. Then if you plug in the workflow for data assimilation, so I have a trained neural network, I get an ensemble of prior models, do the encoder parts, transform into Gaussians. From Gaussians, I can get facies again. From facies, I can do reservoir simulations, get predicted data. Then I go to ASMDA and update the Gaussian representation, the latent representation. With new latent, new facies, new data, new data, new data. This is the data simulation workflow. There is a training before, and there is a data simulation below. And very quickly, just one example, synthetic problem, not real problem. I'm not sure about the time, but yeah, let's just show the results. This is a synthetic problem, so I know the truth. That's the reference, that's the truth. The truth is a model with channels. We call it sinus channels, like fluvial channels. And there is three types of facies. A channel, which is like this yellowish color. Then there is what people call levee, which is the facies surrounding the channels. And there is like a background, which is the facies, which is transparency here, but there is of course a background which has poor properties, so there is not much flow inside this background, but there is some. And this is one prior realization, so it's a model generated before the simulation. This is a posterior realization. And of course, doing data simulation with deep learning, this is a problem we solved with this kind of neural network, right? And it matches data fairly well. And you kind of can see that the result is really nice. You still get channels, well-defined channels. The sequence channel levee background is preserved, so it preserves what a geologist would like to see in a model. If you do the same problem, I'm not showing here, but if you do the same problem directly with ensemble smoother without no parameterization, you get very nice data matches. Matching data is not the challenge anymore, but then you kind of destroy the continuity of the channels. You're never going to see really sinuous channels anymore. You're going to see something smooth representations of channels. You're probably going to see concentrations of high properties, high permeabilities, for example, because channels are related to high permeabilities. You're going to see high permeability regions in the correct places, because data is telling me where I should have the high permeabilities, but you're not going to preserve this shape of the faces. Another realization, again, different channels. All right. Last example, using deep learning for data parameterization. And here I'm concerned about what we call 4D data, 4D time-lapse seismic data, which is sort of a data that is an image of my reservoir in different times. So I take the difference, and then I can see what changed in the reservoir due to production. I can see the water that I inject in the wells going towards the production wells. That's really nice. And I'm showing here like a picture. This is a synthetic problem, but this is a work in the very beginning. By the way, this is a work with a company called Alitrace, the name of the colleagues here. It's a collaboration, of course. And they derived this neural network. This is their work. I just tell things that they are much better with deep learning than I am. I just give opinions and then do other things. But again, it's a sort of autoencoder, but now they are using a pre-trained autoencoder because there is not too many images for the training. And the idea is to get an image and a latent representation of the image. Same idea as before. Why am I trying to do that? And they come up with this example that shows why I'm trying to do that. And the example is basically the following. I got very fancy images of seismic. They are related to a very complicated model called Stanford 6. It's a model with 3 different geological zones. The first zone is one kind of geology called like a deltaic reservoir system. Then there's a second zone with lots of channels. It's like a fluvial system. And there's a third zone with smaller channels, longer channels. But this is like, we got one layer of this model, and this is my seismic. So it's one layer of my model. And then they compare this layer, this image, with other layers of the same model. Each layer is different, but because one layer which is closer layers are correlated, they should be similar in a way. And then they compare using the Euclidean distance between images, which the Euclidean distance is the distance grid block by grid block, pixel by pixel. Why do I care about pixel by pixel? Because the Ensemble-based does that. The Ensemble-based has that quadratic object function, which is, it's not a Euclidean distance, it's a Mahalanobis distance, but it's really close to it. It's a distance in a space of a covariance matrix, but it's a distance, you see, like this one. And if you do a comparison layer by layer, you see the closest one is layer 1, the next closest one is layer 3. Then he got an image that has nothing to do with the geology going on here. It's from a layer down beneath, layer 82, 81, then gets another very strange, then I get layer 2, then layer 114. You see, comparing images, complex images, pixel by pixel, might not be the greatest idea of the world. And if you do the same thing, just comparing the latent representation, you compute the Euclidean distance in the latent space, you get something that makes more sense. You see, the closest one is layer 1, then layer 4, layer 2, then layer 3. All of those have the same sort of geology. Then I run out of this geology, I have something different, but it's still, you can see that's still similar. There are other examples. For this example, both do very well. You see, I'll get models that looks the same. And there is another one here. The lower layers, they have like those channels. Then Euclidean distance does well until it doesn't. At this point, there is no more images like this one. So we have to select another one and select a very strange one. And if you do in the latent space, you get very nice. And then when you run out of those channels, you get things that, still look like channel. You see, it's a different sort of channel, but has the same geology. It's the same geological model. Okay, that was that. Just final comments. Ensemble assimilation, Bayesian formulation. They are efficient and robust for reservoir data simulation, reservoir history matching. They need some tricks to avoid premature loss of variance. When I was preparing this presentation, I had so many things to talk about, and one of those things was what we call localization. These methods, they have one big problem, which is sampling errors. I have 100 samples to compute correlations with models that has 1 million parameters. So there will be sampling errors. So there are lots of tricks people do to improve sampling errors. I'm not again. I didn't discuss this in this talk. There is a really large literature. The main method is called localization, which basically tells me, you know what, for each data point, define a region in which I trust that data and try to confine the change in that region. That's the engineering explanation, but there is a mathematical explanation which has to do with Hamada Schur products, and which makes all the matrices how can I say full rank, which is really nice. I mean, it's a really nice idea. It's an ad hoc idea, but really nice. What else? These methods are in operational use. We've been using Ensemble Smoother ESMDA for data simulation in Petrobras since 2013, 2014, for all kinds of problems. And there are several opportunities for improvements. For example, combination with deep learning or machine learning methods in general. For example, for representation of more complex models. I would say, final words, there are two main challenges today with those methods. One is getting more robust ways of dealing with sampling errors. Localization works really well, but it's really ad hoc. That would be nice to get a more theoretical way of dealing with sampling errors. And the second one is dealing with this kind of model. Okay, I would say that's another challenge. And dealing with this kind of model, deep learning looks like a good idea, but it requires, it requires training. It's not so simple. It's not operational yet. I would say that. All right. Thank you. That's it. Thank you. I appreciate. I'm going to put you again so we can see your faces. Thank you, Professor Álvaro. That's all.
Yeah, well, Dr. Emerick, thanks a lot for the nice presentation. And the floor is open. Should I please ask you to stop the presentation? Okay, thank you. I think the floor is open for questions. Well, I have some questions, but Fernando would like to start. Janeiro, which is around here as well.
I will start with a very simple question. Are you doing it in sort of a real-time simulation, or are you doing a batch?
No, not really. We typically don't do real-time. We get like 30 years of production and try to assimilate 30 years of production. But eventually we have to repeat the process every year because you get new data and then you have to. But it's not a real-time process.
Okay. So regarding the flow model, what we have as a flow model?
What I mean by flow model is, by flow model, it's what we call reservoir simulation. So it's fluid flow in porous media. It's based on Darcy's law. Yeah, sometimes they call flow model, sometimes they call reservoir simulation. I'm very confused.
Yeah, that's crazy. Yeah. I think there's someone online.
Yeah, we have please, Mathieu, go ahead. Mathieu Ducros, please.
I have a question. I understood that the ensemble-based Kalman filter is kind of a trick to deal with stochastic uncertainties embedded into the geological model. Would it, so you said that you trusted your geologist, but it seems that the geologist don't trust himself because he put some stochastic event in his geological model. Wouldn't it be easier to directly treat the geological uncertainties through the deterministic process?
Well, that's a nice question. That's a really difficult question to answer. You see, yes and no. I mean, why? Yeah, it makes lots of sense if I could model the whole geological process and try to do data assimilation in my initial hypothesis of when I build the geological model. But what we resort in practice, what we do is because we don't know the distribution of properties, we treat properties as geological properties as a random events and apply like Bayes' rule to update my belief in model parameters. That's the philosophy behind the scenes. When you do Ensemble smoother, there is one thing that it's really nice is that it doesn't care very much about the number of parameters. The complexity of the problem is related to the number of models, not the number of parameters. So geology can generate different models for me, and I can throw all kinds of uncertain parameters in the process. That gives lots of degrees of freedom for matching data, you see. So operationally, it's easier to do this way.
So, in fact, I have two more questions. I will maybe ask them directly. First, as you use geostatistic to perform your geological realization, how can you be sure that you are sampling well your uncertain space? Because you have no assurance that you are well sampled. And the other question is,
just answer the first question because I want to forget the first question. Yeah, no, great question. I cannot make sure that there is a hypothesis going on behind the scenes, which is I'm assuming that I'm sampling correctly my prior so that I can move towards the posterior. But that's a strong assumption, and very, very often it's not true.
And because from what I understood of ensemble Kalman filters, is that your problem of localization comes from this bad, in great part, come from this part. Not only, but in great part it can come from this bad sampling of the uncertain space.
Oh yes, but you see. That's true. Typically, we don't do so well in terms of prior modeling. It's something we try to survive with. But the problem of localization, it has to do also, even if you get a good sampling from the prior, you still have sampling errors. You still have to do localization. That's one thing. The other thing is, even though it's not possible to make sure, to guarantee that the prior is well sampled, you sort of have some screening tools that can tell you, well, it's at least decent. For example, we can see the predictions from the prior models and see if they span the observations. There are all sort of tricks you do to make sure that the prior is reasonably well defined. And very often what happens is I do a data assimilation, and the end of the data assimilation, the result is not a set of models for predictions. It's a set of models to give back to the geologist and tell, hey, do your job again, because that was not so good enough. That was not good enough. You see, and then we look at the results and revise his ideas and do it again. All right.
Okay, thank you. And last question, then I can let the stage to someone else. With these techniques of reduction of the dimension, like variational autoencoder, isn't it the good way to transform this stochastic uncertainty into a deterministic one? Because we can from this latent space, we can recreate in continuous space some new realization of the geological model.
I think I missed a little part of your talk, but your question, but I think I understood. You are absolutely right. However, that's one of the things why I like variational autoencoders, because they are stochastic networks. I can sample after training. I can still sample the latent representation and get different phases. When I got a well-trained variational autoencoder, I can use as a proxy for geostatistics. For example, I just give another Z vector, a different random Z vector, and given a different realization, which it looks like samples from the prior. Another very nice thing about variation autoencoder is that if I give the z-vector is my sample, is my random representation, and do just a small perturbation in this vector, it gives me another realization that is close to the first one. So it builds like a continuous manifolds of the model. You see, it's really nice. I mean, if you look at the mathematical formulation and look in terms of manifolds, it's really nice. Really nice map.
So thank you.
Yeah, I appreciate the questions.
Well, any other questions? May I? Again, I mean, it's a fantastic talk, and I really appreciate it, and I think all the others have appreciated as well. But how do you see? I mean, I have some couple more general questions. There is a hype nowadays about reduced order models, surrogate models, etc. How do you see they fitting in your workflow? I mean, they're going to be replacing sampling or aids replacing sampling. It's like using a surrogate or even a neural network to generate samples in aids. How do you see this?
Yeah, that's a good question. You see, if you look at the literature on data on history matching, I would say that 80% is based on proxies. All right, it's a way of solving the problem. It doesn't fit. No, it does fit very well in this scenario. I could do data simulation using proxies. That's not my favorite thing in the world. Okay. One cool idea would be because there's sampling errors in Ensemble Smoother, I could generate a large ensemble of proxy models. Because now proxies run fast, I can generate millions of versions of the model, so I can deal with the sampling error. But there is always an approximation that proxy makes. So there's a trade-off. And one other thing is that proxies, they tend to have like the coarser dimensionality. So that's one thing I don't like, because you see, the way we deal with Ensemble Smoother is like we get 1 million parameters, and he does behind the scenes sort of a reparameterization in terms of the space of the realizations. The complexity of the problem is the number of realizations, not the number of parameters. When you deal with proxies, you have to deal with the number of parameters, which is large. So you have to do some sort of model reduction, like you said, and then yeah. But yeah, another just last comments. If I can come up with a really nice proxy of my Reservoir simulation, that's going to work really well. I would not be doing Ensemble Smoother. I would be doing Markov chain Monte Carlo. Because MCMC, that would sample better than Ensemble Smoother.
Yeah, you made that remark when you're presenting. Yes. Then now in the end, I understand the point. I mean, it's basically a trade-off. If you can get a very nice proxy, you can trade, MCMC and sample. Otherwise, you cannot. So it's again, we come back, or how good is your proxy, or how good is a reduced order model in the whole workflow? Yeah, I got your idea. Yes.
Yep.
Yeah, because since you're a practitioner, we have to listen to you. Otherwise, it's very easy to say that to hear the academics, people pushing for new methods without realizing the full range of complexity in applying them in the real workflow. Yes, that's a very interesting point. Thank you. Any other questions?
Yes, I have a small question for.
Yes, please
Emerick.
go ahead. Please introduce yourself, Janeiro.
Yes, my name is Janeiro from Chemical Engineering here in the COPPE. It's a very, very nice and beautiful presentation regarding to all these algebra formulations you present in this very didactical way.
Thank you. Nice. Thank you.
My question is regarding to the assumption of the smoother that you have mentioned, that it's just similar to the common filter, or the extended common filter, and also the regularization, like the Tikhonov regularization for that. But the strong assumption that's worked quite well for linear models, for GM as linear, and you have strong non-linearities in your model. This assumption, maybe mainly regarding the sampling, and how you work with this motor that's based on this linear assumption, and what do you think would be another alternative to something like when you do filtering, like particle filter sampling, not the like Kalman filter.
I see. Nice question. Well, the first part of the question is what we do iterations. That's why we do MDA, multiple data assimilation. So ensemble smoother doesn't sample well because it's assuming linearity, so we do iterative. So there are several iterative versions of ensemble smoother, most of them based on that analogy with Gauss-Newton. Okay, there's different ways of deriving these iterative ensemble smoothers. And regarding particle filters, they are really cool because they don't need this assumption of Gaussianity. They don't need this assumption. You're just giving weights to models according to the distribution, the pursuit distribution. So it's really cool. It does make almost no assumption. However, they fail if you have high dimensions. And when I say they fail if you have high dimensions, there is so many people that are going to complain about these comments because there are so many things people are doing to improve particle filters. All sort of resamplings, strategies, but I would say, but that's a personal opinion, they're still not operational for large-scale problems. But that's a personal opinion. That's a personal opinion. But they are really cool because they don't make assumptions about Gaussianity. No, nothing. That would be much better than ensemble smoother.
Yes, it's another compromise of sampling. Sampling is the problem.
Yep.
That's true.
Yep.
Okay, thank you very much.
I think we have another question from the floor. Eugênio Fortaleza, please introduce yourself and go on.
Good afternoon. I'm Eugênio Fortaleza from University of Brasilia. Congratulations, Emerick, for the great presentation. I would like to know if you could say the computational cost comparing this deep learning that you are using now and the traditional filtering methods.
Yeah, thank you. Yeah, that's a good question. That's Eugênio. By the way, nice to see you again. You see, we tried ensembles. We tried deep learning for two problems. Yeah, the first problem was facies, representing facies. The way we do now is based on lots of samples of facies, 40,000 samples of facies. So training, it's complicated. It takes, for that problem, it takes like a few hours in a cluster of GPU. So it's something I'm still a little bit skeptical, but it seems that there are alternatives for dealing with that. Okay. For the second problem I showed for seismic, we're actually using one alternative, which is using a pre-trained network. What they did was essentially they took this VGG network and put another layer just for a fine tuning. So it runs like in 5-10 minutes. They do this just fine tuning, and it's okay. It's done. So far it works well. There is one limitation on that network, which is they are two-dimensional. I mean, they are 4 photos. So I have to look at data as a layer and not as a three-dimensional data like they really are. Models are three-dimensional. So let's see. Yeah. But I would say there is a space for doing lots of things. Yeah.
Great. Thanks a lot.
Thank you.
Thank you. We have another someone in front of the floor called Bessa, willing to ask you some questions. Please go ahead, Bessa. Introduce yourself and go on. Oh. Okay. Well. Anyway. Well, we have from Alessandra Davolio Gomes. Please, Alessandra, go ahead. Introduce yourself and go ahead.
Okay. Hello, everyone. Hello, Emerick. Yes, I'm Alessandra from Unicamp. And yes, I have a quick question. It's actually a curiosity for you, Emerick. Well, as you might guess, I'm going to ask about for the seismic data. Okay, I think I understood what you're proposing, but I think you're trying to deal with the problem of comparing images, right? As we always see it. So my question is, wouldn't it be simple or easier just using another metric I mean, you could just use like a binary or a ternary transform your images to something easier to compare, and then, I mean, I think it maybe to be faster for if even if, well, especially because you're going to add this into the data assimilation process and so on.
Yeah, thank you for the impossible to answer question. But yeah, no, you're absolutely correct. However, that's my guess, Alexandre. That's my I think that's gonna work better than binary or three images for two reasons. One, binary is really difficult to couple with ensemble smoother because you have to come up with the covariance matrix of data errors. So binary is really difficult to do in this scenario. And with deep learning, we're going to get a continuous representation in the latent space. That's one reason. Another reason is that it seems to me that binary is good, but there is variations of values of data. And I think deep learning would be able to get difference between not only positive and negative, but gradations in positive values. You see what I mean? It's still continuous representation. That's what I'm trying to say. In terms of time, at least what we're doing now, it doesn't take no time anymore. I mean, it's a pre-trained neural network, so yeah, it doesn't add much complexity to the problem.
Okay, that's good.
But we still have to come up with a way of transforming the noise of data to the latent representation as well, because you have to represent the matrix. But it seems to be possible because it's just you get the noise in the inputs and then go to the latent representation. It seems to be feasible to do.
Okay. And then just take the opportunity. Another question: when you do
just one second, Alessandra.
Yeah, sure.
We cannot hear you very well. Your voice is too low.
Oh, sorry. Yes, I'm having some troubles with my mic. I don't know why. Sorry. Can you hear a little bit better now?
Yes, it is.
Okay, I'm gonna talk a little bit louder. Yes. So, Enrique, when you do this, I mean, similar process for the facies model, my what I was wondering is that can you still guarantee the correlation with the petrophysical properties? I mean, you know, if you have three facies, then you have good, bad, and medium quality rock. So do you lose this correlation between facies and can you still guarantee they will be there in the models?
I know what you mean. What we do a trick that is the same thing we do for truncated Gaussian. We update, we have like facies and its representation in the latent representation of facies. And you have a grid of porosity of the good facies of facies 1, another grid of porosity for the facies 2, and a third grid of facies 3. And then we update everything together. And when I do a reservoir simulation, now I have to build a model. I generate my facies, and then I do like a copy and paste. This is facies 1, so get porosity from the grids of facies 1. This is facies 2, and get porosity from facies 2. Then you're going to see that the models, they always have high permeability or high porosity at good facies.
Okay, good. Yeah.
It's actually it's the same thing that the geostatistics does facies modeling. Yeah? It's the same strategy.
Okay. Okay. Thank you very much, and thank you very much for the very nice talk.
Thank you. I appreciate your comments.
Thank you. Let's see if I have anything else in the chat. No, some people are leaving. I would like to ask you that I can stop. I would like to stop recording and close the formal session. But I'm here to stay. If Dr. Emerick can continue for a while, I think we can continue here almost as much as we want. But I have somehow to close the recording, the formal section, and stop recording. All right. Okay. So to be formal, let's thank our speaker. And well, I hope you have. Let's thank our speaker for his excellent talk. And I hope to see you all in our next meeting. And you'll all be going to be part of our mailing list. So please, drop by as if it happens to. If you happen to get interested in the subject that we're going to be presenting, our speaker we're going to be presenting here. Thank you for coming. I'll stop recording right now.
Okay.